Thanks for the introduction. Also, I'm very happy to be invited in this nice workshop, not just academically full of interesting talks, but as well as full of interesting dinners and lunches. Today I'm going to tell you about quantum advantage, which can be pursued by so-called Hamiltonian simulation. Yeah, but even though the title of this conference is involving machine learning stuffs, yeah, I'm not an expert in machine learning area, but I like to make a contact between what I'm working on so far and machine learning side in the end. So I know many of you are not working on this quantum computing business, so I like to make my talk friendly to the newcomer and also those who are not familiar with quantum computing. And so please don't hesitate ask me any question during the talk. Yeah, so this is the brief structure of my talk. I think just till few years ago, many quantum computing people argued that we can reach soon the quantum supremacy. But somehow this terminology, quantum supremacy, got really a huge attack from the classical computation theorists. So I think nowadays, even quantum computing people almost gave up this terminology. So they became more modest to use this kind of quantum advantage alternative terminology. So that's why I decorated my talk with this alternative terminology to be seen modest person. Yeah, anyway, so I'm going to tell you what this quantum advantage means briefly, and also the basic elements in the quantum computing or quantum processor like qubits. And also I'm going to tell you how can be embedded in reality as a form of quantum annealer or digital quantum computer. And to achieve this kind of quantum advantage, there can be many strategies. But today I'm going to focus on more physics motivated or physics inspired strategy. Those are so-called Mexico problem, which can be implemented on a Ising model-based quantum annealer, and also another type of problem called spectral problem, which can be revisited with digital quantum simulation. Also, if time permits, I'm going to tell you its summary of what quantum advantage is. It basically means a computational advantage we can take when we use quantum algorithm and quantum processor in solving a certain problem over their classical counterparts. For instance, this graph shows x-axis is the size of problems we need to solve, and the y-axis is the complexity. It can be a requirement resource to solve the problem, or simulation time, or number of steps of the process we need to take to get the result. And given the classical computer or classical algorithm shows exponential dependency to solve this kind of problem. Yeah, and the history of quantum advantage is basically a journey to achieve or devise many nice quantum algorithms. So this is a brief history of the quantum algorithm. So it refers to the way of thinking in order to solve mathematical problem or computational problem with the usage of qubits or any other quantum processes. So as we all know, the Feynman basically is the father of quantum computing. So he basically briefly sketched the idea of quantum computing a long time ago. And after that, many nice people suggested interesting idea to achieve exponential speed up in solving certain problems. For instance, Shor factorization suggested how to factorize integers into primes with the quantum computer in a quicker way. And also Grover search achieved the square root advantage in searching problem. And also HHL solution means how to solve linear systems with the quantum computer. And they achieved also another polynomial speed up in this, so in solving linear systems with the quantum algorithm. However, even though those kind of algorithms are very interesting, but there was huge attack by classical computation theorists and those kind of attack can be summarized at this kind of keyword called quantum memory. So this means that even though we can solve all the things in a polynomial time very effectively if we use the quantum computer, but when we load the data on a quantum computer, that kind of loading process or state preparation process should take exponential time given the size of the problem. Yeah, so this kind of quantum memory was suggested like 2 decades ago, and then many people got really shocked about this kind of thing. And someone argues that this can be easily devised in a real world soon. So this is not a huge problem. However, theoretically, this is again an annoying problem. So I think usually, even though this kind of all the computational problem was considered kind of route to achieve quantum advantage, but as a physicist, we can take another detour to achieve quantum advantage. So in this talk, I'm not gonna focus on this kind of computational problem, but instead more physics-inspired problem to achieve quantum advantage in another way. Okay. So yeah. Yeah, so now let me explain you what quantum computer is, basically. So qubit is the two-level quantum system, and it's a basic element in a quantum computer. So as we all know, it consists of basically two levels, and then we can use this kind of basis, 0 or 1, or spin up and down to represent its state. And usually, quantum computing people prefers 0 and 1 notation to up and down notation. And one easy way to memorize this 0 and 1 convention is to memorize this one-line equation. The eigenvalue of with respect to this Pauli Z operator is either +1 or -1, and then -1 to the n, then we can easily memorize this 0 and 1 convention. Yeah, anyway, unlike classical bits, this kind of qubit can allow superposition, but superposition is not everything of a quantum computer. Actually, we need to gather this qubit to form a quantum processor, and those kind of gathering is called basically done two ways, and those kind of gathered qubit is obviously called qubits. Yeah, so there are basically two ways to operate this kind of array of qubits. Yeah, one is called quantum annealer, which is a collection of interacting qubits, and on a quantum annealer, we can usually tune its interaction strength and couplings. And there's another way called quantum gates or quantum circuit or digital quantum computer. And these are, as suggested in this figure, consist of basically an array of qubits. And also, in addition to that, we can arrange many quantum gates, which is the analog of the logical gates in a classical computer. So these kind of gates can act on each qubit, not just a single qubit, but 2 qubit, 3 qubit, multi-qubit, to manipulate the state of the quantum states prepared on the qubits or array of qubits. So as I mentioned, there are not just the single qubit gates, and multiple qubit gates can introduce so-called entanglement, which is the genuine feature of quantum computing. So if we look at this kind of two arrangement or two settings, then gate-based circuit looks more versatile. However, in the NISQ area, noisy intermediate scale quantum computing era, this kind of circuit-based architecture is more vulnerable to the quantum noise or decoherence noise. So current era, I think annealer is a bit, in some sense, it's a bit worthy, even though it's not versatile. It's specific to solving some special kinds of problem. However, it's more robust under the decoherence or other types of noise. So far, many people use this kind of annealer as well as this kind of circuit-based architecture to solve interesting problems. Yeah.
The main difference between the annealer and gate is the equidistant interaction. Main difference. No interaction in the quantum gates and interaction.
Maybe types of interaction. So quantum gates, we can introduce many different gates. So many different type of interaction can be introduced. Yeah, but however, on an annealer, there are finite types of interaction you can introduce. Also, there's a range of its strength we can reach. So it's more limited. Yeah, I think that's a huge difference. And there's an additional difference in the problems we can solve in each type of device, but I'm going to tell you it later. Yeah, I think before introducing a few interesting quantum algorithms, I think the key essence of the quantum algorithm would be summarized into two parts in single slide with two contents. So the first one is quantum parallelism, which is induced by superposition and entanglement nature of the qubits. Yeah, so because n multiple qubit can store the information about 2 to the n dimensional Hilbert space. So naturally, parallelism is allowed on a quantum computer. So if we devise a nice way to measure the final states, then we can extract the information quite efficiently, then we can treat all the information simultaneously. So naturally parallelism is achieved on a quantum computer. That's called quantum parallelism. And another key interesting aspect, in particular for physicists or chemistry people, is that quantum simulation. And this is exactly what Feynman devised the idea of the quantum computer. So because the nature is governed by quantum mechanics or quantum mechanical principles, then if we think of some way to simulate the nature, then it would be natural to think of computer, which is made of quantum elements. So condensed matter people actually, got focused on this kind of thing from long decades ago, many decades ago. So they introduced many interesting ways to simulate condensed matter system on a quantum computer or quantum annealer. And interestingly, high energy physicists also began to work on this kind of thing. So we can simulate Schrödinger model or any other lower dimensional theory, on a field theory, if it's lattice regularized on a quantum processor these days. Yeah, so the following two are, as I mentioned, the way to apply quantum computer to interesting physics problems. So the first one will be the max cut problem. So this problem is a bit subtle, so let me explain you briefly, one by one. So this is basically graph theoretical combinatorial problem. So let's think of this kind of graph made of nodes and edges. And in this max cut problem, we classify these nodes of this graph into two kinds. For instance, we can color some nodes as red and some nodes as yellow, like this or like this. And then we can basically count the number of edges which connect the different types of nodes. For instance, these edges, these edges connect yellow and red. So we count this one. And also these edges connect yellow and red. So we also count this one. But this edge, if you look at another one, then this connects red and red nodes, right? So we don't count this. And similarly, if you look at this edge, this connects yellow and yellow, so we don't count them. And we collect all the edges which connect different colored nodes, then its number can be, in case of this cut, 1, 2, 3, 4, 5, 6, right? It becomes 6. So the Mexican number for this graph, given this kind of classification, becomes 6. However, if we divide the types of nodes into this way, like color red onto the upper sides and color yellow as lower sides, then the max cut, which connects yellow and red nodes, becomes 1, 2, 3. So this gets small. This kind of coloring shows a smaller number of max cut. And max cut problem is to maximize this kind of max cut number given the assignment of the yellow and red to each node. So this can be summarized in this sentence. How can you divide the vertices in a graph into two groups so that the length between two groups becomes maximal? So this is the max cut problem. And one interesting solution is this. We can rearrange this kind of 6-node graph into this way and then divide this way. Actually, this is equal to this graph. So so this is the answer to this kind of max cut problem for this graph. However, without a rearrangement, it's quite hard to figure out this is the real answer to the original problem. So let me rearrange this kind of problem into another way. So if you look at the problem more carefully, then we can translate this kind of problem to the kind of optimization problem. For instance, we can assign, as I colored nodes into two different colors, we can assign number either +1 to the -1 to the nodes. For instance, let's assign +1 to the yellow colored nodes or white colored nodes and -1 to the red colored nodes or black colored nodes this way. And then the number of the edges which can connect different group of nodes is counted with this function. Here, Wij is just the adjacency matrix, which shows the connection status of the graph. So if the two nodes is connected, then this Wij, which is defined between two nodes, becomes 1. And if not, then Wij becomes 0 between the two nodes. And then if we compute 1 minus Xi, Xj for same color nodes, then Xi times Xj becomes either just becomes +1 because either it can be the 1 times 1 or -1 times -1. Then we can end up with 1 minus 1, so it vanishes regardless of this Wij. However, if both nodes belong to different kinds, then the product xi and xj becomes 1 and -1, so -1 overall. So 1 minus this vector becomes 2 in the end. And then Wij, the number of edges, can contribute non-trivially to this value, the quantity we want to maximize. And then, yeah, so this is kind of objective function in the optimization problem. So to solve the Mexico problem is translated to optimize this kind of, to reach the maximum of this kind of target function. Yeah, and interestingly, there's another, so on the other hand, we have, as I mentioned, there is a so-called annular, which can embody the quantum computation device in real world. So basically, it's the real-time machine of the Ising model. So this Ising model, as we all know, is governed by this type of Hamiltonian. Zi, Zj is the spin operator, Pauli Z operator defined to each side, and Jij is nothing but the coupling. Yeah, if we allow the nearest interaction, then Jij will be non-zero only at the nearest neighboring combination. But in general, we can assign more general Jij distribution. Yeah, so I'm going to connect the two. Yeah, and if you look at carefully this Hamiltonian Jij and Zijj, and again go back to this kind of optimization function, then you can see the analog between the two. Zi, Zj, the Pauli spin operator, can be mapped to either xi and xj, the coloring signal, and Jij will be mapped to adjacency matrix Wij. And this is just a constant piece. And if you ignore this Wij times xi, xj is exactly equal to the Hamiltonian. So, it depends on, right. But I think in more general, not just two dimension. I think more general dimension, if the graph agrees with the two, so to solve this optimization problem is equal to basically to figure out the ground state of this Hamiltonian, Ising type Hamiltonian. And adiabatic quantum annealing is exactly doing this kind of business. To given the Hamiltonian, which is described by Ising type this way, then all the adiabatic quantum annealing is doing the finding out the non-trivial ground state for the non-trivial distribution of the coupling Jij. So in general, this is very hard. Even though 1 or 2 dimensional, there is an analytic solution for nearest neighbor interaction. But in general, Jij can be defined not nearest neighbor sites, but widely separated sites as well. Then it's quite hard to solve. So the general strategy for the annular people is that you consider very simple Hamiltonian in their initial stage, and then consider adiabatic procedure, which moves one ground state of the one simple Hamiltonian to the another ground state of the very complicated looking Hamiltonian. So for instance, we can consider this kind of really simple Hamiltonian, which only carries the nearest neighbor interaction on a single line. So this is just a one-dimensional one, but you can draw any different thing. Anyway, this is just a simple Hamiltonian. So we know its ground state is nothing but 0, 0, 0, 0 something, in which all the spins are aligned in the same way. And then by so-called adiabatic theorem, we can tune the coefficient of the interaction, this Jij term, very slowly and very carefully. Then it is known that ground state, this state is transferred to the another ground state of the more complicated Hamiltonian. This is so-called adiabatic theorem. The intuitive picture behind this is something like this. If we have this kind of complicated potential whose ground spot is known to be here, then if we begin from the relatively simpler potential shape, where we know the exact location of the lowest energy, and then if we move this kind of string or rubber band very slowly and very carefully, then this ball, which is located at the ground spot, lowest energy spot, minimum of the potential well, then slowly moves to the another minimum point of the potential well, even though the shape of well becomes more complicated. Yeah, obviously there are so many loopholes in this kind of theorem. So there are mainly two caveats associated with this. One is the level crossing phenomena. So if we quickly move this kind of rubber band or strings, then there might be degeneracy, energy degeneracy can appear, or this kind of continuous mode can appear. Then this kind of thing may cause huge error in the end. So while tuning this kind of potential well from the beginning to the end, we should be careful so that we do not face this kind of level crossing or energy degeneracy in between. And another caveat is the initial overlap. So classically, the starting point should be ground state of the initial simple potential. If we begin from this site, then this ball would go either this way or this way while we change the shape of potential well, right? Right. Yeah, it's true. So in quantum case, it's exactly, it's not necessarily for us to set the initial state as the exact ground state of the initial potential. That's also a good point if we go from classical to the quantum. In classical case, we should identify the lowest energy spot, the bottom of the potential well exactly. However, due to tunneling effect, as we mentioned, in quantum mechanics or in quantum annealing device, it's allowed to set kind of offset from the exact ground states. Yeah, for instance, if we begin from this state, if there's a non-trivial overlap, like something like this in its initial wave function, then there's an annealing algorithm which allows us to find the final non-trivial ground state in the end. Yeah. This is one way quantum annealing thing. And there's another interesting application I'm going to introduce, and this is more related to my work with Masazume. So this is the roadmap of the IBM, showing the growing industry of the digital quantum processor. So according to this roadmap, which was suggested in 2 years ago, at 2025, we can use this kind of 4,000 qubit quantum computer. But unfortunately, this is not realized in the real world. So I think this is postponed to maybe 2 years later. Yeah, so there's a 2 years gap from this graph, from this roadmap to reality. But anyway, it's not a huge gap so far. And also, if we plot this kind of number of qubits available now, so far, then you can see there's kind of Moore's law or something like exponential growing in the number of qubits available versus time. Yeah, anyway, so many people think there's a promising future in the quantum industry. So as a high energy physicist, many of high energy physicists agree to think of there must be a way to apply this kind of new wave technology to our usual business. So there's kind of many meetings at CERN or Fermilab which gathers high energy physicists and discuss how can we apply this kind of new technology to solve many interesting high energy physics problems, not just in experiment, but also theory as well. Yeah, so digital quantum simulation is one interesting way devised in such a meeting. So it comes from the idea that the natural embedding of Hamiltonian time evolution of quantum system is allowed on a quantum processor. As I mentioned, digital quantum processor is made of two different things. One is the qubit, which stores the quantum states or quantum information, and the gates, which manipulates the states of the quantum states on a qubits. And then we can map each qubit or arrays of qubits to the degrees of freedom we think of. It can be field theory degree of freedom, or many-body degrees of freedom, or just a wave function on a discretized space. And then the action of quantum gates, unitary action of quantum gates, can be mapped to the action of unitary time evolution on a real quantum system, the quantum system of interest. Then what we need to think of is which process we are going to simulate on this kind of device. So to do digital quantum simulation or to apply this kind of technology to interesting problem, we need to answer these kind of 3 questions before proceeding. So first, we need to decide how to encode quantum fields, for instance, or interesting degrees of freedom to the spin qubits on our hand. And second, we need to think of a way to encode interactions into discrete sets of gates. As I said, there are a set of elementary gates, so not arbitrary unitary operator is exactly mapped to the gates. So there is a discrete set of gates, so we need to kind of do translation between the real unitary complicated operator to the set of elementary gates. And third, most importantly, we need to decide which kind of process is interesting or is worth simulating on a quantum processor. So in particular, if one's interested in spectroscopy, which is to solve energy gap of the interesting quantum system, then we need to determine what kind of physical process depends on the energy gap. So that by simulating this kind of phenomena, one can get the information about energy gap from the outcome of the simulation. Yeah.
Why do you say quantum field instead of anybody?
Right. So this should be said like lattice fields into spin qubits. So we need to somehow discretize all the things, right? Yeah. Right. That's more correct terminology. Yeah, sorry.
There is very famous problem of discretization. One of them, especially for forming that is.
You mean doubling thing?
Doubling
Yeah, that's true. Yeah.
I think this problem also happens here.
Exactly. Yeah, it's still, there's still such a problem. Yeah, but conversely, it's the reason why so many lattice people now working on quantum computing business. Yeah, somehow, usually that kind of Nielsen-Ninomiya no-go theorem, such a thing in lattice community can be detoured by, it's no-go, so we cannot penetrate it. Yeah, but we can devise an interesting way to detour such a thing, giving up locality, for instance, or giving up some, how can I say, some subtlety in the dispersion relation. Then we can think of some fermionic system, which can be defined on a, Obviously, its continuum limit is non-trivial issue. So if one's interested in energy gap problem, so how to diagonalize the Hamiltonian, then one of the options of our algorithm is stems from this Fermi-Golden rule. So basically, it governs transition rate from initial state to the final state when we introduce additional perturbation to the Hamiltonian, which is sinusoidally oscillating at given frequency omega. So we have some definite Hamiltonian H, and in addition to that, we can introduce additional quench to the Hamiltonian, which is governed by this way. Delta V is a certain operator, and sine omega t specify its frequency. And then the initial state can be moved. Even though initial state was the eigenstate of the original Hamiltonian H, then it jumps to the another state F with this kind of probability. So it's basically, this golden rule is made of two different pieces. One is called selection rule, and another is usually dubbed this frequency matching condition. So let me explain you one by one. So selection rule part is nothing but the what is this? This inner product between initial and final state with respect to this additional operator, perturbation operator delta V. And usually if a certain state carries some conserved quantity, then final state should carry corresponding conserved quantity depending on the type of operator you insert, right? And frequency matching conditions suggest we should take care of the energy. And that's why I introduced this kind of golden rule in solving Hamiltonian energy eigenvalue problem. And it suggests when there is a matching between external frequency and the gap of the initial and final states, quantum transition can occur. So quantum transition does not occur at random frequency, but it occurs at particular frequency, which equals to the energy gap. And that's why we can measure energy gap by introducing additional quench, as I will introduce more, as I'm going to explain you a bit more later. So this is basically this kind of logic was allowed us to, for instance, determine or observe this kind of hydrogen energy eigenvalue problem long time ago. And so this is more specific, more detailed feature of our picture cartoon showing the detail of our algorithm. So initially, we should prepare the ground state of the system. So going back to this slide, so this I initial state becomes ground state in our case. And this F, the final state, would be another excited states of our Hamiltonian. And so during the certain process, we should prepare the ground state initially, and then later introduce quench delta V or the perturbation to the system, which oscillates in a time. And after waiting for a second, and then we measure the final state, and then see whether the initial ground state disappeared or it still exists in the end. If it exists, then we can say there is a no quantum transition from initial ground state to the other excited state. And that means this particular omega regime, there is no corresponding energy state, excited states. However, if the initial state disappears, then it strongly signals that there is an excited state at that particular energy, which satisfies the selection rule condition with respect to this delta V. So we can conclude there is a corresponding certain non-trivial quantum states at particular omega. So basically, this algorithm or this process, quantum simulation process, is made of three different things, as I mentioned. One is ground state preparation, and second, the quench time evolution, and third, the measurement.
Quench simulates the gate, like the circuit.
Right. All the process will be mapped to the array of gates, right? Actually, this state preparation is also non-trivial, so there should be corresponding gates which can realize the non-trivial ground state of the Hamiltonian. So the first stage can be implemented with gates, this kind of thing. So initially, as Anila people began all the thing from 0, 0, 0, 0, certain type of states, which was the ground state of the nearest interacting Ising spin. So we can also do something similar like that. So if we think of this kind of Hamiltonian, actually, I didn't present the interesting Hamiltonian, but anyway, it's a subset. I mean, the Hamiltonian H has some certain subset, which was suggested drawn here. So if M0 is really, really huge, really large, then this term dominates the Hamiltonian. Then the ground state of this Hamiltonian becomes like spin zero, spin up, down, something like that. 0, 1, 0, 1, 0, 1, something like that. Such an alternative states. Anyway, it has clear analytic expression for the ground states. Then we prepare that state initially, then introduce kind of interpolating Hamiltonian from H0, which has a simple form and simple expression for the ground states, to the non-trivial H, which has complicated form and complicated form for the ground states. Usually the ground state, analytic expression of the ground state of this kind of H is not known. Anyway, thanks to the adiabatic theorem I mentioned, we can prepare the ground state at this level. Then we can discretize the time evolution, and such a discretized time evolution can be mapped to the discrete set of quantum gates. And such a discretization is usually the Suzuki-Trota time evolution in quantum computing business. And there exists a map from this kind of discretized time evolution to the set of quantum gates. Then we can apply quench time evolution successfully on our system. And this is one result. After all, we can measure whether ground state survives or not. So this is basically measuring this quantity. We can prepare a vacuum ground state initially and introduce quench time evolution in the middle. And then after all, measure the vacuum state again. But what we measure is basically probability, not this kind of amplitude itself. So we need to take square. And this is what we measure. So under this type of quench, whose spin qubit expression is given by this way, then we can see, so here black or blue color suggests there still exists vacuum, and yellow and green color means it's quite rare to observe the vacuum in the end. So, and all the solid line signals the exact diagonalization eigenvalue, and the x-axis of each graph suggests that the parameter in the Hamiltonian. So we can vary one parameter in the Hamiltonian, and we can scan all the frequency regime to see whether the excited states exist or not. And as you see here, we can successfully identify the lowest excited states encoded in this yellow line, orange line. And also here, more excited states can be observed by tuning the additional dressing factor to the quench operator. So this kind of algorithm can has many advantages, but also drawback. For instance, we can directly explore the high energy regime if we just increase the frequency omega, as I suggested. And also, one can filter the quantum number naturally because the Fermi-Golden rule carries the, the selection rule part. So it somehow distinguish different quantum number by that kind of selection rule pieces. So we can choose a certain operator and weights to filter the quantum number, specific quantum number excited states. Obviously, there's another drawbacks. One is the ambiguity on whether transition really occurs or not. And also whether there's ambiguity in whether accumulated error contaminates the qubits or not. So there must be other statistical analysis involved to really analyze whether there exists excited states or not. Also, it is quite not good for super precise estimation on the energy gap. As we can tune the omega bit certain, but actually the Fermi-Golden rule was the lesson from the perturbation theory. So it's not the exact result. So in reality, there is a broadening around the real exact omega. So there's a broadening effect, so it contaminates the result. Actually, it's already shown here. So the exact value is something like this, but here another, the neighboring cell becomes green. Yeah. So that kind of, there's a certain drawback in this algorithm, but however, there's a still advantage. So I think I believe this is one way we can pursue quantum advantage with physics-inspired ideas and problems. Yeah, so interestingly, yeah, thankfully time remains. So let me add one additional section about machine learning, as the title of the conference involves machine learning for quantum field theories stuffs. And so let me briefly introduce machine learning application for the Hamiltonian simulation. Yeah, obviously there are many interesting ways to apply quantum computing or quantum computing technology to many interesting problems. But let me focus on just one way. But this is not the only way. There are so many ways to apply. So if you are experts in machine learning, then you can have a chat with quantum computing guy. Then I'm sure that there must be new project interesting. Yeah, so this is most of the talk, I will talk about ground states or state preparation or Hamiltonian thing. So let me focus on this part. Yeah, also in this part of my talk. So this is so-called machine learning aided state preparation. So there's a concept called the neural network quantum state, which means neural network based representation of certain wave function, usually ground state wave function. Yeah, and for instance, restricted Boltzmann machine architecture network can be used to realize this kind of NNQS neural network quantum states. So if we go back to the initial problem, let's think about this kind of 4-qubit system, and we have complicated Hamiltonian, which is made out of these 4 qubits. Then the problem is we want to solve the ground state wave function representation of this many-body system. Then what we should know is actually the amplitude, this kind of thing, the coefficient of the wave function given the basis xi. Right? This xi should be more complicated because there's 2 state bases, 0 and 1 for each state. So this becomes more complicated combination. But anyway, let me allow this kind of shorthand notation for that. Then we can think of some network structure, neural net structure inspired by this one. So upper layer, we have this kind of nodes whose number is the same to number of qubits this way. And either nodes can carry 2 different values, 0 and 1, reflecting the 0 and 1 basis states of each qubit. And there's a hidden layer here below. And this hidden layer also can take 2 different values. But this is kind of, this is not restricted to the Z2, and we can more generalize to higher, more degenerate, how can I say? Yeah, more general system, more complicated system for hidden layer. Yeah, anyway, so our task is because we are interested in the coefficients of this one, our task is to identify certain coefficients given the representation for the specific basis. So when we assign certain numbers, 0 and 1, binary number to the nodes, then this network can give us certain value. Then that value will be interpreted as the coefficients of the this ground state wave function. As you see, this kind of process or network can be replaced the approximation method I introduced earlier, adiabatic algorithm. And this is more detailed for the this RBM-based neural network quantum states. So we can define this kind of energy functional, which is made of this way, right, this way. So Wij is the kind of weight which connects each different nodes, upper layer and exposed layer and hidden layer this way. So this is just number we are going to train. And Xi and Yj are all the binary integers associated to either quantum state basis or hidden layer basis. And we can define this kind of neural network quantum state as an exponential of like a partition function with respect to this energy thing. Then if we assume at certain, in the beginning, we assume, what we are gonna do compute is this kind of amplitude. So given the X basis coordinate, basis information, this will spit out some certain complex, certain number. And the number is carried by this kind of partition function thing. And then we sum over this Y states, all the possible states this hidden layer nodes can carry, and we can end up with this kind of functional thing. Then with respect to variational algorithm or minimization process with respect to a certain loss function, in this case, the loss function will be nothing but Hamiltonian of the quantum system. And then we can tune this Wij parameter, or we can train this parameter so that Wij is well estimate the ground states, well approximate the ground state psi. Yeah, such approximation method also carries pro and con, nice thing and drawback. One nice thing is we can capture hidden feature of the wave function. So even though the size of the system system becomes larger, then we can think of more efficient network structure to approximate the ground states. However, there's also drawback because as all the variational algorithm or variation method does, the complexity estimate for the training process is quite hard. So I think this is common feature between adiabatic algorithm and variational algorithm. Yeah, anyway, there's a kind of drawback. Yeah, but I think this is one way to achieve quantum advantage. Yeah. So this is the summary. So as I said, quantum advantage is the many people's goal these days, and many-body physics can be a platform for the quantum advantage. And one example is a combinatorial problem like Max-Cut problem. Such a combinatorial problem can be translated to physics problem, as I mentioned. And also there's another genuine physics problems we can solve with quantum computer. For an instance, it's a gap problem. And there's another interesting class of problem called observable computation problem. For instance, we can compute entanglement entropy, to be precise, Renyi entropy using qubits, and also stabilizer entropy using qubits. So such an information theoretic observable is more easily observed on a quantum computer. Yeah, so it's an interesting way. And there's many ways I didn't mention, but there are many ways to apply machine learning technology to quantum computing business. So I encourage people to work together if one works on machine learning and one works on quantum computing. So yeah, this is end of my talk. Thanks for listening.